Hello, I'm going to explain this example. So, figure 2.14. Here is the circuit which I'm going to draw again, and the question would be to drive the relationship between the input voltage V and the output voltage VC, the voltage across the capacitor, second capacitor. We have two of them. So if you have watched the video about the simpler circuit that we had in figure 2.13, so this will be a little bit more complicated and takes a little bit more time and calculations. So let's start. We are going to use two approaches to get this relationship. The first one, we are going to look at the first law, Kirchhoff's first law, and we are going to look at the nodal analysis. And then the second one, the second approach would be to look at this one. I think for this video I stick to the first approach, and then I record for another approach, so you have them in separate videos to watch. Now, here is the circuit. We have voltage supply passed to our first resistor, and then we have a junction here. We have one capacitor here, and then at the other junction we have one resistor and another capacitor. So I'm calling this one R1, R2, and C1 and C2. So this would be input, and this, the voltage across this capacitor would be the VC or the output. Okay, so I'm calling this point A, and I'm calling this point B. So you would know that the voltage across this capacitor, capacitor C1, has relationship with the current that is flowing here. So I'm calling that, if I call the current that is coming here, I'm calling it I1. That would be the same current that comes to this junction. So that would be the same, I1. And then at point A, some of that will go through the C1 path, and some of that will go through the R2C2 path. So the one that goes through R2C2, I'm calling it I2, and the one that goes through C1, I call it I3. So Kirchhoff's first law says that the current that comes inside this node is equal to the current that is going outside that. So if I call that nodal analysis, it says that I1 is equal to I2 plus I3. So that will be the initial equation that we would write. Now, let's look at some of the components that we have here. If I want to write the relationship between only R1's voltage and current, so if I want to just draw that part again, I'm drawing a circuit, and I'm going to draw it again. So I have, sorry, that's my daughter. That would be my V, and that would be my point A, and I'm calling the voltage here VA, and this is the resistor R1, and the current that is flowing is I1. Now let's just look at the relationship that happens here. So we know that any typical resistor has the V is equal to IR. Now in this case I want to name it, and the potential difference across this voltage, across this resistor, would be the difference between the V and VA. So for that reason, I should write V minus VA. That would be the voltage across this resistor. And the I that is flowing through that resistor is I1. So I have I1 here and R1. Now, if I want to get I1 from this equation, I just need to replace a little bit, and then that will give me I1 is equal to, I just divide both sides by R1, and then I will have V minus VA divided by R1. I hope that is clear. Okay. Now let's look at C1. I'm going to draw C1 again. I don't want to use same color. Do I have another color to use? Yeah. Okay. I'm just pulling that here. So this is my point A, and this is my capacitor, and this is my point B. This is C1. The current that is flowing is I3. Now let's look at this component on its own. If I want to write equation that is representing the relationship between the voltage across this capacitor and the current that is flowing through this capacitor, that would give me this equation. Again, if I want to refer to the table, so you would see here that I have two equations that shows relationship between the voltage and current through capacitor. So I can write I is equal to C derivative of voltage over time, or I can use integration. So I'm going to use this one here because I want to have V on one side or derivative of V on one side. That's the reason I'm using that one. It seems that, am I focusing here? Okay. Do I need to press the focus again? All right. Now, so I will have I3 equal to, what is the voltage that I have here? C1. And when I'm looking at the voltage across this capacitor, I'm looking at the voltage for point A, because my B will be the ground. So the difference between these two, the potential difference, would be my V, the voltage of point A. So I should write dVA over time. I hope that is clear, because B, if I refer to the main diagram, that is many times we miss it, but here is actually ground. So the voltage for the ground is 0. So that is the relationship between the capacitor C1. Now, I want to look at the C2. So what can I write about C2? This is particularly important because the voltage across C2 is our output. So that we really want that. So if I just draw it, this is C2 and the voltage is VC, or our output, and then the current that is flowing through this capacitor is called I2. Now let's write that. It will be similar to this equation here because it is single capacitor and it has a voltage and it has a current. So let's write that. And we stick to VC because that is the output that we want. Now I2 will be C2 derivative of VC over time. Okay. Now, what we can write now, we can rewrite the nodal analysis that we have here, and we can replace I2 and I3 and I1 inside this equation. Or what we sometimes say, we substitute. So we are going to put equivalent of I2 here, equivalent of I3 here, and equivalent of I1 here. I'm going to write it down again. So this nodal analysis is going to be rewritten. So I1, I know that I1 is V minus VA over R1. V minus VA. That's on the left side. On the right side, I know that I2 is C2 derivative of VC over time. And then for I3, I know that it is equal to C1 derivative of VA over time. Now, please note that R1, C2, C1, they're constant. So what is changing here, what might change actually, is our input V, VA, VC, VA. Now, so far we have this equation that has multiple variables, but the plan is to have something that looks like this. We have something that multiplies in V, our input, in one side of the equation, and then we have something that is multiplying in VC plus or minus something that is multiplied in derivative of C, and then something that is multiplying in second derivative. So that is the plan, the target is to get that equation sorted. For getting to that point, I have to replace some variables here. I have the V, I'm happy with my V. R1, there's no harm of that, it's constant. VA, I don't like it. It should be something that depends on VC. Here, C2 is fine, dVC dt is fine. The other word here, I have derivative of VA. I don't like it this way. So I want to replace VA and derivative of VA over dt in equivalent that has VC or some order of VC inside. Now let's continue and see how we can get to that point. So from the circuit, I kind of have to draw it again. This time, because I want you to be confident about having different types of representation for resistor or other components. I'm putting this rectangle shape, but I'm referring to the same resistors. Okay, so this is the circuit. Now I'm going to look at what is happening here. The current that is flowing here was I1, and this one was I2, here was I3, and this is my point A. Now if we look at the relationship between the potential difference of these points and the current that is flowing through it. So if I call this one VC, now if I look at this component on its own, I take it out. this is VA, this is VC, it is R2, and the current that is flowing through is I2. So potential difference is equal to the current multiplied in resistance. So VA minus VC, that's the different potential difference, and then I have I2, R2. If I want to get VA somewhere and VC in the other way, my plan is to find a relationship to replace VA with something that depends on VC. So I'm just pushing the VC the other side. I keep the VA, I2, R2, and plus VC. Now here I can replace this little guy here, I2. I have something that already depends on VC based on that. And what was that? Can anyone point out? So I have this relationship here that I can use to replace I2. So it is C2 dVC dt. And I'm going to keep the R2 because it's a constant. And that would be one step closer. Now I'm going to do derivative of both sides. So I'm going to do derivative of each word. Let's see what I get over time. So derivative of VA over time is equal to, so constants are factored out, and then I will have second derivative of VC over time, and then I will have derivative of VC over time. So this is useful because I'm going to use that in next few minutes. Now I'm going to look at this equation that I ended up here, and I'm going to replace the relationships that I found for the derivative of VA over time and the VA itself. So from here I can use this equation for replacing the VA, and I can use this equation for replacing the derivative of VA over time. So if I call this 1 and 2, I'm going to use 1 and 2 to replace inside my equation that I got earlier. Okay, I'm going to rewrite this and then we take it from there. Alright, so what I had was, let's make a line here. So I had V minus VA over R1 is equal to C2 derivative of VC over time plus C1 derivative of VA over time. And remember that I said we don't like to have VA, we want to have C or some order of derivative of VC. I'm just double checking that I wrote everything correctly. C2 dVCT, C1 dVA, and dt. Yeah, correct. Now I'm going to replace that. So what do I have here? It will be a little bit big equation, so I try to write it a little bit smaller. I'm just checking my focus is fine. Yeah, alright, so I just break this down. So it will be V R1 minus VA R1, and then the other side would be C2 dVc plus C1. So instead of dVA over time, I'm going to put entire equation 2. So this will have a big multiplication in the entire R2 C2 second derivative of Vc over time 2 and dVc time. So this is that one, and then that is that one. Okay. Now, what else I can do? I can here. It's all okay. I like it. Yep. Everything looks good. The only problem that I have is this guy here. That should be replaced. Now, for doing that, I'm going to use the equation number 1 here. So, V R1 minus. So, if I want to write the entire division R1, so it will be a big part here, and that will have R2 C2 dVc dt plus Vc, and then everything will be repeated. C2 dVc dt plus, I can multiply this, so it will be C1 R2 C2 second derivative of Vc over time, plus and plus, everything is good, so C1 dVc dt. Remember what I explained? The plan is to have something multiplied or divided or whatever in V in one side, and the other side should be Vc or some order of Vc with some constant multiplied or divided. So in that respect, so I'm okay here. I just need to factorize and make it a little bit look better. In the other side, I'm okay. I have Vc, dVc, and V here. So I need to keep the V and kind of write it a little bit cleaner way. So if I just multiply and divide everything and break down everything a little bit better, and this minus will go inside, so I will have and if I keep dVc and factorize it, so it will be dVc dt in C1 plus C2 plus C1 R2 C2 second derivative. Okay, now I have something that is multiplied in my derivative, first derivative, and I have something that is multiplied in my second derivative. But I should bring all this stuff the other side. That will complete the job. So I'm just writing the final equation here. The final equation will have V divided by R1, R2, C1, C2 on the left side, and on the right side it will have R1, R2, C1, C2 multiply in Vc and there is a plus 4 second derivative of VC over time, and this big equation has R1, R2, C1 and C2, and the bottom and the top has all the combination of my constants, R1 C2 and R2 C2, and that is multiplied in dVc in dt. So that would be the final equation. I'm going to show it in book because that's written way cleaner than mine. So that is the equation. That's the end. This is first approach. For the second approach, we're going to use Kirchhoff's second law, and I'm going to explain that in a separate video. Okay, well, that is not a good handwriting. I should try to write it again. Well, to get from this point to this point, I want you to try it yourself, but I'm going to explain it in next video if you couldn't figure out yourself.